Now, so far, we've looked at different ways of keeping data in a repository. One way could be based on a list, and if we're making something based on a list, the best that we can expect of that is a theta in performance on average. If we use a tree structure, then we can expect a log n performance. If the tree is a binary tree, then that base of the log will be base 2. Now, suppose we can do better. Is it possible to have a constant time access? Let's say we put something in a repository, and then as soon as we want it, we don't have to wait any length of time. We just request it and it comes out immediately. Is that possible? Is it possible? That's like the Holy Grail, isn't it? That would be too good to be true.
Yeah. Then why would we do the rest?
Actually, there is a strategy that attempts that. And the way it does it is that it looks at the data. And from the data, it then tries to get the address of where the data is stored. Possible? If we did that, if we had people registered for a course and we're told that everybody is restricted to not having the same name, or let's say you take only one person with the first initial, and the person with the name starts with A sits over there, the person with B sits over there, the person with C sits over there. So as soon as I call the name, you know exactly where that person is. Now, hashing does exactly that. What we try to do with hashing is to link the data that's being stored with some address. And the strategy isn't that complicated if as long as you decide to put down the item that you're storing in an address based on the data. That way, when you're picking it up, you look at the data and then you go to get it at the place where you put it down. Now, normally, if you're doing that, you would normally have some kind of a small part of the data that you'd use as a search key. So that's all we mean when we refer to key valid pairs later. You would have a search key, and then once you found the key, then you actually get the value that you are interested in getting. Alright, now in the problem that we're supposed to work out, we got a hash table that has a size of 7, then we got a hash function. Now, normally, once you are hashing, you would apply some kind of function to the data to get the address. And once you've got the address, you are going to store the information in one or two strategies. The simplest one to remember the configuration of is closed address hashing. In closed address hashing, once you determine the address, then you don't go anywhere else. You know that you're going to find the data in that address. Now, it is likely in a real hashing scenario that several things can hash the same address. If that happens, we call it a collision. And the way that we handle collisions in closed address hashing is to build a chain from the address. So, starting from the point that we hash to, we have a linked list leading off. So a search could be a search through a linked list, but at least we know the initial starting point. In open address hashing, we can say our options are a little bit open to getting another address. Now, we would put the data in the table. We first try to put the data in the address that we hash to. But if there's a collision, if something's there already, we need to find somewhere else. And a common way of finding something else is probing through the array. If you're doing linear probing, we will be going up in certain steps. If you're using step size 1, we're looking at consecutive positions to see if we find a free space. And we store the data in the first free space. Of course, the searching will have to take into account that we may have been doing that when we were saving. Alright, so in this example, we have a hash table of size h, and our hashing strategy involves a function that looks like this. Function on first name is equal to 5I1 plus I2 mod H, where I1 is the first initial, I2 is the second initial, and H is the size of the array.
That's 5I1.
Right, 5I1 plus I2 mod H.
Okay.
In this case, we're told that H was 7. Now, the question also specified that the initial values were based on the positions of the numbers from the start of the alphabet. So A is 1, B is 2, etc. Alright, so if we have that, we're now going to ask to put some data into the array. So the data that we need to put would be and we're told that the key consisted of the first name and the last name. So we'd run our hash function on these two values, on these two fields. That would be the key, and the rest of it would be the value that you would be retrieving. And if you're watching the news, Dogfoot has nothing to do with anybody that may be on the news. So, we're first asked to state or to draw a diagram that would show how this data will be represented using the closed address hashing strategy. How do we start? You're lost. Okay, where did you get lost?
Which one started closed?
Right. It would be useful to first determine the addresses, wouldn't it? So let's run the hash function, determine the addresses, and then we can decide to put them in, given the strategy. So, hash address would therefore be equal 5 times J is the 10th letter in the alphabet. Plus B is the second letter in the alphabet. And that would be equal to
7, that's 3.
We all agree, right?
Yeah.
For this one, it's 1 times 5 times 1 plus C, third letter in the alphabet. That's equal to 8 mod 7. For this one, D is the fourth letter in the alphabet. F is the sixth letter, right?
So just
5.
Yes, sir.
You agree with 5?
Yes, sir. And this 4. And 6. And 6.
So we have the addresses. I'm going to need that space. I'm just going to put down the addresses here. So I'm going to put in position 3. If I'm writing it down, just making sure that I don't forget it. Now, it's critical when you're hashing that you don't generate an address that doesn't exist. So that's why the mod function is always useful. That would limit the addresses that would come out of the hash function, and you can limit the address to the amount of memory space that you have available. Now, it's also good to spread out the addresses. The perfect hash function would actually distribute all keys that are coming in evenly. Of course, the perfect hash function may not exist. So what you may find is that some hash functions may give more collisions than others. If it gives more collisions, it's not really a desirable hash function. If it gives less collisions, it's a really good hash function.